Okay. So we have discussed 13th and 14th group elements now. So yesterday we have discussed about halides of group 13 and group 14. So let us make one question on that. Which of the following undergoes okay, which of the following undergoes hydrolysis? First option CCl4, second one SiCl4, and C BCl3, and D all of them. So what's your answer? So what I am saying, you need to treat these halides with water. Okay, so what will be the product formed? First of all, tell me whether they undergo hydrolysis or not. This is the question. Yesterday I have told you about SiCl4, if you remember. Okay, so SiCl4 will undergo hydrolysis. Okay, why it is undergoing hydrolysis? Because silicon means which group element? I mean 14th group element we know, carbon and silicon, both of these. But it has only 2p2 electronic, I mean 2s2 2p2 here. This one is having 3s2 3p2, and the next one is 3d empty, 3d 0 orbital is there now. So to that empty orbital, the lone pair electrons are donated from here. Okay, so this is coming like a nucleophile, this is an electrophile. So these silicon is electrophile, chloride will comes out now. Okay, so like that, how many chlorines are there? 4. All four chlorines are replaced by OH groups of water, so that you will get it as SiOH4. So I told you the name of this compound also yesterday, silicic acid. What is this? Silicic acid. So and 4 H plus ions and 4 Cl minus ions form 4 HCl. Okay, this is fine. Now what about this one? This is also belongs to same group now, but it will not undergo hydrolysis. Why it will not undergo? See, I told you there is an empty d orbital here in the silicon, so that water can attack here. But here there is no empty d orbital now, so there is no vacant orbital with the carbon right now. So therefore CCl4 will not undergo hydrolysis. Okay, you can say it as inert, and this is labile if you want. Okay, and what about BCl3? See, BCl3 also contains one vacant p orbital now. That's why we are saying these as electrophiles, if you remember. BCl3 is an electrophile now. So now what happens if you add water? So this water will be act as a nucleophile, enters into this empty orbital. So like that, each time chlorine can be replaced by OH group. Like that, how many chlorines can be replaced? All 3. So that you will get it something like this, BOH thrice. Or you can write it as H3BO3. So what is the name of this compound? Orthoboric acid. What is that? Orthoboric acid. Okay. Now what is the like acidic nature? I mean, what is acidic nature in the sense, how many H plus ions, or what is the basicity of this acid? How many H plus ions it can release? No, it cannot release 3 H plus ions. It is a Lewis acid, I told you yesterday, if you remember. So why I am saying Lewis acid? So BOH, OH, OH, like this we have, and one vacant orbital will be there now. So it can accept a electron pair here. Therefore H3BO3 is an acid. But what type of acid? It is a Lewis acid. It's not a proton, like a proton donor here. Okay, these H plus ions cannot be released here. Okay, don't say that these are dibasic acid, tribasic acid. Okay, so what I am saying, it is a Lewis acid. So what are the species undergoing hydrolysis? Only B, C. Okay, not A. Remember this. Okay, this is an important question. The next, today we will be discussing about 15th group to 18th group. Okay, so these are the things. Have you tried any questions after the class from 13th, 14th? Okay. Okay, see what are the groups we have remaining? 15, 16, 17, 18 we have. Yesterday 13, 14 are done. Okay, so now what are the things we need to know? First of all, in these groups, what are the elements we have? What are their properties, like periodic properties, radius, size, volume, then next density, how ionization energy varies, electronegativity varies. These are the properties, the trends they are asking. And what are the factors affecting them? And some compounds. For some compounds means, for example, nitrogen, what are the compounds of nitrogen? We have like ammonia, nitric acid. These are some important compounds. No? We need to look into it, and what are their properties and their applications. Okay, these are the things to study from this chapter. Okay, yeah. See, P block elements means how the electronic configuration should look like. NS2, NP, 1 to 6. Now if we observe in complete periodic table in the P block side, there is one element won't follow this electronic configuration but lies in P block only. Helium. Okay, remember this. Okay. So up to 13th group we discussed. So now in the 15th group, what are the elements we have? Nitrogen, phosphorus, arsenic, antimony, bismuth, moscovium, MC. Okay, these are the elements. Okay, what is the atomic number of moscovium? 115, 115. Okay, so now like it is easy to remember. It is easy to remember. First two are non-metals, next two are metalloids, next two are metals. Once again, first two are non-metals, next two are metalloids, next two are metals. Okay, non-metals, metalloids, metals. Okay, so now these elements, I mean these group 15 elements are also considered as nicogens. What is it? Nicogens. What do we mean by that? Their compounds, their hydrates of group 15 are poisonous. Okay, see, poisonous. Nicogens means poisonous meaning. So few elements and their hydrates are poisonous, hence they are called as nicogens. Okay, this is the reason for it. Okay, now so now what happens to the periodic properties? Down the group size increases, atomic radius increases, ionic radius also increases. Okay, next atomic volume means also size only, no? It is also increases, density also increases. Okay, why density increasing? See, down the group what happens to mass? Mass increases, now mass by volume is density. So increase in mass is greater compared with the volume. That's why density also increases. So in the short form you can write AR, IR, AV, AD. All of them are increasing. Okay, next. What happens to ionization energy down the group? Size increases, na, easily we can remove the electron. So it means ionization energy decreases. So ionization energy down the group decreases. Okay, now if you remember, in the exam definitely you will get one question on ionization energy. Particularly they are asking about period elements like 2p series elements, 3p series elements. Let us consider 2p series elements. What are the elements we have? Lithium, next beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So highest ionization energy is for, as we move from left to right, what happens to ionization energy? Increases. So neon is highest. Okay, always noble gases. Next fluorine. Okay, between nitrogen and oxygen, nitrogen. Why? Half-filled electronic configuration. So you can write neon, fluorine, next nitrogen, oxygen, next carbon as it is, between these two things, beryllium, boron, lithium. Okay, so same series, I mean same order will be followed even in the 3p series also, 3p like third period also, but different elements like here sodium, below this magnesium, here aluminium, silicon, phosphorus, sulfur, chlorine, argon. Okay, same order will be followed like this. Okay, the changes will be observed here and here. Okay, what is the reason for this? This is called penetrating capacity of s orbital. This is half filled electronic configuration. These are the two reasons we discussed in the periodic table. Okay, that's it. So you can say group 15 elements have higher ionization energy than group 16 as well as group 14. Done with this order? Okay, what about electronegativity? Down the group increases. Down the group decreases. Electronegativity. What about electropositivity or metallic nature? Increases. So first two are nitrogen, phosphorus, non-metals. Next two are metalloids, metals. Okay. Now write the order for this boiling point and melting points. So what is happening to the boiling point? Check once. Increases down the group. See, boiling point increases with increase in molecular weight. So increases down the group, but antimony is greater than bismuth. Which is greater? Antimony is greater than bismuth. So just change this order and write. Okay, next. Melting point. Melting point increases up to arsenic, then decreases. So melting point increases up to what? Arsenic, then decreases. Okay, nitrogen to phosphorus, phosphorus to arsenic increasing, then next decreasing, right there. See, all elements shows allotropy. All group 15 elements shows what? Allotropy, except nitrogen. Allotropy means existing different forms. Like for phosphorus, P4 white phosphorus, black phosphorus, red phosphorus will say. Like that for, but nitrogen does not have that allotropy nature. For carbon we discussed yesterday, na? What are the three allotropes we discussed? Diamond, graphite, fullerene. Okay, next one is anomalous properties of nitrogen. See, in the P block elements, these second period elements are there now, like carbon, nitrogen, oxygen. They show some different properties compared with the other elements of respective group. It means compare with the nitrogen family, I mean all the elements of nitrogen family, nitrogen have some different properties. Phosphorus, arsenic, antimony, these will be having some property. But nitrogen shows something different from the other elements of that particular group. Like that, carbon also shows anomalous behavior, oxygen also shows, like that second period elements are there in the P block elements that shows anomalous behavior compared with the other elements of respective group. Okay, so now why it is showing like that? So we know nitrogen is more electronegative due to its high electronegativity. What is the reason? Due to its high electronegativity, small size, it has small size or not in the respective group. The next, due to high ionization energy, and also what about its electronic configuration? 2s2, 2p3. Do we have anything like 2d0? No. So due to this unavailability of d orbital, it can show maximum covalency. How much? Covalency. It means how many orbitals are there in the valency, ma? Subshells are 2, but orbitals I am asking. One is s orbital, remaining 3 are p orbitals now. So how many orbitals are there in the valency? So that many bonds an element can make. How many valency orbitals are there? 4. So it can make covalency of maximum 4. It means it can form maximum of how many bonds? 4 bonds. Whereas other elements are there now, like phosphorus, if you consider, what is its valence electronic configuration? 3s2, 3p3, 3d, 0. Right now, so now it has empty d orbital, so that phosphorus can increase its valency beyond the 4 also. Like it can show valency 5 and maximum it tends to show even 6 also. What is the example for 6? PF6 minus. For 5 it is PCl3, PCl5, like that you can write. PF5, PCl5. Okay, so do you got what do we mean by covalency? Maximum covalency of nitrogen is how much? 4 for nitrogen. For other elements they can extend. Even same story applicable in other series elements also, carbon family, like that also. Okay. So now nitrogen can form p pi multiple bonds. Okay, what type of bonds it can form? P pi multiple bonds. For example, N2 molecule if you consider, how it will be? Nitrogen, nitrogen. There will be one sigma bond. The next pi bonds are formed by, 2 pi bonds are formed by what type of overlapping? P pi overlapping. So that's why I am saying nitrogen can form P pi multiple bonds with itself or smaller elements like it, or elements with similar size. Similar size elements, you tell me. For example, carbon, you say. Carbon, nitrogen can make multiple bonds now. Like this we are writing cyanide means. So here also what type of bond it is? P pi. Whereas other elements are there now. Whereas other elements of the group. What are the other elements? Elements of P, phosphorus, arsenic. These elements won't have ability to form what? P pi bonds. They won't have ability to form P pi, but they can form something like D pi bonds. D pi bonds. Because they have empty orbital, empty d orbital is there now, so that will be utilized by these higher elements, and they can make D pi. Whereas nitrogen can make P pi. Okay, so same story in carbon family also. Carbon can make what type of bonds? P pi bonds, but not D pi. Okay, this is arsenic. Done up to here? What are the reasons for anomalous behavior? Once again tell me. High electronegativity, small size, high ionization energy, or unavailability of d orbital. Okay. Next one, we know nitrogen triple bond is there, right now. Now what I am taking is nitrogen single bond I am considering, phosphorus single bond I am considering. Which is having greater energy I am asking. Single bond, not a triple bond. When you consider only single bond, NN single bond is weaker than PP single bond. I am not comparing the multiple bonds. What I am comparing? Single bond. Next, chemical properties. So tell me, what is the valence electronic configuration? Just now you have told NS2 NP3. So 5 electrons are there. In order to become octet configuration, how many required? 3 more. So nitrogen or that group 15 can take 3 more electrons and can show -3 minimum oxidation state. How much? -3. So the minimum oxidation state shown by the group 15 elements is how much? -3. Okay. Now the general oxidation state will be like +3. Okay. And what is the highest oxidation state? We will see +5, because all these 5 electrons if we remove becomes +5. Okay. Now tell me, nitrogen maximum covalence is 4, maximum oxidation state is +5. Okay. Remember these two terms. Okay. So down the group, what happens to metallic nature? Metallic nature, down bottom elements are metals right now. So metallic nature increases means metals are electropositive. Electropositive means they need to have positive charges. If we put negative charges, they are unstable or less stable. So what I am saying, tendency to show -3 oxidation state down the group decreases. Can I say like that? Because minus charges cannot hold by the metals. That's why tendency to show -3 oxidation state decreases down the group. Okay. So due to its metallic character. Next. Now what are the other two things we have? +3 and +5. See, if I only remove this NP3 electrons, what is the oxidation state you will get? If I only remove P electrons, +3. Okay. If I remove all electrons, +5. Yesterday we discussed inert pair effect. What do we mean by inert pair effect? The reluctance of NS electrons. It means these NS electrons do not like to participate in chemical reactions. Okay. It means only these P electrons are participated. Okay. So this inertness increases down the group right now. So the bottom elements try to show what type of oxidation state? Only +3 oxidation state. Okay. Top elements can show +5 oxidation state. Now what I am writing here, stability of higher oxidation state, it means +5 oxidation state decreases down the group. What is the reason for that? Inert pair effect. So now if I show you two ions like this, so what will be the order? See, already I have mentioned anyways order also. So down the group like arsenic, antimony, bismuth I have. So now what happens to the stability of +3? +3 lower oxidation state now. See, there is two oxidation states, +5, +3. So +5 down the group, what happens to +5 oxidation state? Inert pair effect increases now down the group. This is least stable. So this bismuth wanted to show what type of oxidation state? Only +3. Okay. So down the group, +3 oxidation state stability increases and +5 oxidation stability decreases. So these two orders I have written. So make a short note of this. Don't write all the theory. Just write important points only in that orders. Okay. So now what is the stable oxidation state of bismuth? Plus +5 +3. Okay. So down the group, +3 oxidation state stability increases. So the only well-known characterized compound of bismuth with +5 is BiF5. It means all other compounds are not existing. Why? Because bismuth wanted to exhibit in which type of oxidation state? Bottom element, no? So it wanted to be in +3 only. So the only one well-known compound is which one? bismuth pentafluoride. ఎక్కడుంది? ఇప్పుడు దీని మీద ఇట్లా ఎలక్ట్రాన్స్ ఉంటాయి కదా, వీటి మధ్య రిపల్షన్స్నే ఇంటర్ ఎలక్ట్రానిక్ రిపల్షన్స్ అంటారు. నెక్స్ట్ so we know what is the highest electronegative element in the periodic table? Fluorine. Second highest oxygen. Third highest nitrogen and chlorine. What are the two elements? Nitrogen and chlorine. So since nitrogen is electronegative element and it's a small size with a high electronegativity, nitrogen can show different oxidation states. Okay, it can show 10 different oxidation states now. How many different oxidation states? 10. So starting from -3, where we can see -3 in ammonia. What is the oxidation state of nitrogen? -3, because hydrogens if you remove it will get a -3. Okay, so like that from -3 to +5 all the oxidation states are shown along with -1/3. Okay, so -1/3. Where -1/3 is possible? Like this I am writing HN3 minus. So now see H plus N3 overall as minus. So for 3 nitrogens what is the charge you are seeing? -1. So for 1 nitrogen how much it will be? 1/3, -1/3, like that. So what are the oxidation states from -3 to +5? Okay, along with that -1/3. So total how many? 10 different oxidation states are possible for nitrogen. Okay, now what is the maximum oxidation state of nitrogen? +5. Okay, so now look at this. All the oxidation states of nitrogen from +1 to +4 can undergo disproportionation. Disproportionation means same element undergoing oxidation and reduction. See for example nitrous acid we have taken. HNO2 means what is the oxidation state ma? +3. So now this +3 can have possibility to convert into +5, like +5 means higher oxidation state. Okay, HNO3. Okay, and can undergo lower oxidation state up to -3 also. Here it is forming +2. So can I say this element is undergoing disproportionation reaction, both oxidation and reduction? Yeah. So now what are the oxidation states possible for to undergo disproportionation for nitrogen? So +1 to +4. All these species can undergo disproportionation in which medium? Acidic medium. Okay, next. The next slide is important. We can expect a question from the next slide itself. Okay, see when group 15 elements react with hydrogen, they forms what? Hydrates, like it is forming ammonia here. Okay, like this will get hydrates. Now what are the group 15 hydrates we have? Like NH3, PH3, ASH3, SbH3, BiH3. So I can say these are the hydrates of group 15 elements, right? So please listen here, we can expect a question from this itself. Okay, once again, these are the hydrates of group 15 elements. Now they will ask you about the stability of these hydrates. Okay, see here, nitrogen small atom, right now, down the group what happens to the size? Hydrogen size, what you can expect? Hydrogen first, we'll be seeing at the top now, so it is also smaller size. Okay, if the elements are with similar sizes, the overlapping will be effective and the molecule will be stable. Right now, if the overlapping is effective, the molecule will be stable. So now down the group, what happens to the size? Size increasing means that overlapping will be effective or less. It means that bond is easily broken now. So now what happens to stability of hydrates down the group? Decreases. So which is most stable? NH3. You got the stability order. Okay. Then next one they will ask you about solubility. What I am saying? Solubility. See, solubility in water. What about nitrogen, hydrogen? More electronegativity difference is there now between nitrogen and hydrogen. This bond is more polar, means polar compound soluble in polar solvents. Yes or no? So ammonia is more soluble. What I am saying? Ammonia will be more soluble. So as we go down the group, what happens? That solubility decreases. So soluble in water, ammonia soluble in water. So down the group hydrates, what happens to the solubility? Decreases. All these hydrates are toxic in nature. What is the name of this group? Nicogens. Why we are calling them nicogens? Hydrates of these group 15 elements are poisonous. So you can say them as toxic nature. And down the group, what happens to the toxicity? Increases. So this one is more toxic. Toxic nature increases down the group. Okay, and these are pungent order with toxic nature. Okay, remember. Next, down the group, what I told you about the stability, thermal stability? Thermal stability decreases. Okay, remember. The next one, listen. NH3 is there, like this. See, all of these hydrates are having lone pair electrons now. Like this, lone pair electrons are there or not? If there is lone pair electrons, we can say they can donate lone pair electrons. So I can say this is a Lewis base. Yes or no? They will ask you about the basic nature of these hydrates. What is the basic nature order for these hydrates? They will ask. So just remember, down the group basic nature decreases. What I am saying? Down the group basic nature decreases. So what do you think about this statement? I am asking only about basic nature. Look at this. Down the group, why that basic nature decreasing? This is the question you should get. Nitrogen with 3 hydrogens like this now. Next one, phosphorus with 3 hydrogens. Next, S, H like this we have. Do you remember the hybridization concept we studied? What is the hybridization of this nitrogen? sp3. So sp3 with 1 lone pair, 3 bond pairs means what is the geometry we feel? Trigonal, trigonal pyramidal. What is this? Trigonal pyramidal. What is the angle you are seeing here? 107.8 or around 5 degrees you can say. Okay. Now if I move from here to here, this angle also, what you expect here? What is the angle you can expect? Almost the same angle you may expect. But you know, in reality, when they did calculation, experimental data, they found it as 93. How much they found? 90. And they went for this one. It is found to be 91.8. Okay, and like that they went for this. It is around 91 point something like 3. This is around equals to 91. So what happening to the bond angle down the group? What happens to the bond angle down the group? Decreases. Bond angle what happening? Decreases. So first element is how much? This NH3, 107. Down the group it is decreasing. Now remember, see, I am saying p orbital will be like this now. Another p orbital, if I write like this, it will be, because px, py I am saying. So px means like this, y means like this, z means like 3 coordinates will be there now. So what is the angle between 2 coordinates? 90 degrees. 90 degrees now. It means here if you observe the hydrogen bond angles also, you are seeing around the 90 degrees only. It means this bond having nature of p orbital nature. What is the nature of these orbitals? P orbital. In which cases this p orbital nature is there? From phosphorus to the bottom hydrides. All of them are having what type of nature? P orbital nature. Why they are having p orbital nature? How I am saying? Because their bond angle is almost equals to 90 degrees, because p orbitals also have how much angle? 90 degrees. So what is the nature of this bond? S orbit, S character or P character? P character. So now what happening to the this element and hydrogen character of this bond? Down the group P character increasing or decreasing? P character increasing now. Now where these lone pairs will lie now? Because we have one s orbital, remaining 3 are p orbitals. Okay, so 3 bonds means all these 3 bonds are having what character? P character. Now the lone pairs will be in which orbital? S orbital. So more S character, more is the electronegativity. It means that lone pairs will be stays with the metal only. That's why who is having more ability? Only nitrogen is having ability to donate this lone pairs. All of these elements are having less ability to donate their lone pairs. So that's why, which is more basic I am saying? Ammonia. And down the group that basic nature decreases. So which is more basic out of all these things? So now tell me, all these orders you tell me. Stability ఏమవుతుంది down the group for the hydrides? Stability decreases down the group. Okay. Now what I told you, what about bond strength, bond dissociation energy? Down the group ఈ bond ఎలా ఉంటుందమ్మా? PH, NH, ASH like this if you write. What happens to this bond nature? Decreases na. So bond dissociation energy decreases. So which is stronger bond out of this? NH. So more energy, less energy, very less energy, lower energy like that. So bond dissociation energy also decreases. Next, Lewis basic nature, what I told you? Lewis basic nature decreases down the group. Decreases down the group. Next, what about bond angle you have studied? Bond angle decreases. Okay. So now reducing nature. Reducing nature means what? Definitions for reduction means ability to donate electrons or ability to donate hydride ions, like addition of hydrogen. What is that process? Reduction. So if I say these hydrides like NH3, BiH3, which bond is weaker here? NH3 bond, NH bond or BH bond? BH bond is weaker means H minus ion comes from which one? This one or this one? BH. So it is donating BH minus ion easily means, can I say this is a stronger reducing agent? Yeah. So reducing nature down the group, what happens? Increases. Okay. So these orders are very, very important. You have a lot of questions on these orders itself. So once again, stability down the group. Next, bond dissociation energy decreases. Next, Lewis basic nature decreases. Bond angle decreases. Next, reducing character increases. Why it is increasing? Because ability to donate H minus is more for BH, because it is a less stable. Next. When it comes to boiling point and melting point, what I am saying next? Boiling point and melting point. Boiling point, melting point should increase with increase in molecular weight. What I am saying? They should increase with increase in molecular weight. So which is having highest molecular weight? The bottom one, right now. So it means what should be the order? Like this, something like this. Yes or no? What I am talking about? Boiling point and melting points. See, nitrogen hydrogen bond is electronegative bond now. So it means it can form hydrogen bond. Which one? Ammonia can form what type of bonds? Hydrogen bonds, due to the electronegativity difference. So due to the reason of this hydrogen bond, its boiling point and melting point is greater than what we expected. That's why the overall order will be like, you just bring this nitrogen ammonia to here. What is the normal order? Down the group, what should happen with molecular weight? Increase. So bismuth hydride should have highest boiling point and the least one should be NH3. But what I am saying, the resultant one is you bring ammonia and keep it in the middle. Why we are keeping it here? Because of its hydrogen bond. Because of its hydrogen bond. See, boiling point depends on two factors. First factor is what? Molecular weight we discussed. And more than this, you need to also check intermolecular forces. Intermolecular forces means, see, boiling point ante entamma, this is a molecule A, this is another molecule we have. This is a solution. Let us say water only you are taking. These are the water molecules you have. If the intermolecular forces between them is more, means can we separate them into gaseous phase? It requires higher energy, higher temperature. So I can say boiling point will be high. So that's where ammonia boiling point is greater when I compare with this. Why? The intermolecular forces between ammonia molecules is strong. What is the reason for that strongness? Hydrogen. So that is the reason. Okay. So similarly, what you expect for the melting point also down the group, melting point increases. Exceptionally, who should be having highest one? Ammonia. Why ammonia? Same. Intermolecular forces are more here. So overall order will be like this. Okay. Now once again tell me what is the boiling point order? Here I will write pH3, ASH3, here NH3. Please highlight this. Next, SbH3, BiH3. Okay. Next one, melting point. Order will be same. You bring this here. That's it. Remember these two orders, melting point and boiling points. Okay. Next. Up to here everything is clear about the hydrates. Yeah, you can expect a question from this discussion. So similar discussion will be there in the 16th group of hydrates also. Okay. Do you remember that bond angle concept? What I told you for NH3? 107.5. And the next pH3? 93, around 93 I told you, if you remember. So it means what you need to understand, when the angle is around 109.5 or 107.5, we are saying it as a tetrahedral geometry, I mean sp3 hybridization, and particularly if I ask for the shape, you are saying it as a pyramidal. Okay. Here you should not say it as sp3 hybridization. For which one? All other hydrates of 15th group are there now. You should not say them as sp3. Why? If it is sp3 hybridization, should be pyramidal geometry with what is the angle? 107. But how much angle they have? 93. So that's why other hydrates of 15th group except NH3 does not have hybridization concept. What I'm saying, they should not have hybridization concept. This pH, what is the character of this pH? It's a pure p orbital, not sp3 orbital. Because if I ask about this one, you should say this is bond formed by sp3 hybridization. What about this bond? P character. But that's why this p, this p, this p around the angle, around like angle will be seeing around 93, not an sp3. Okay. So all hydrates except NH3 considered as Dragos compounds. What I am saying? Dragos. Drago compound, like he is a person. He told that except ammonia, all other hydrates of group 15 does not show hybridization. Okay. And their pH bond character will be of p orbital, not sp3 orbital. Okay. Remember these 2 points. This is more than extra discussion. All orders done. Okay. There are some questions on this you can solve after the class. Next. Okay. So whatever the story I told you about Dragos compounds and all, it will be here. See what I told you, for NH3 sp3 hybridization, for all other compounds no hybridization. So now what I told you about the bond strength decreases down the group now. So like this, decreasing or not? Okay. Next. It means which bond can be easily broken? BiH. So its bond dissociation energy, bond energy will be least for BiH. Next. So the same story is applicable for this one also. If I ask for the bond angle here, you tell me. Here itself we will finish some discussion of these hydrides. Bond angle will be more for which one? H2O. And then next H2S, like this. It means polonium hydrogen bond is there na, this is weaker bond because of large size difference. Okay, so its bond dissociation energy minimum, highest for H2O. And you can say hybridization here, and you should not say hybridization concept here in the other hydrogens, hydrates of the 16th group, similar to the nitrogen family. Okay. Next, here there we seen about basic nature now. Here it is acidic nature. What I am saying here? Acidic nature. So you should say acidic nature increases down the group. What I am saying? Acidic nature increases down the group. Okay. Okay. Next, what are the bond angle values I given you? First one 107.5, the next 93, next 91.8, 91.3, 91. So now what happening to the bond angle down the group? Decreasing. You already written that orders, no need of writing all this. Next one, reactivity with oxygen. See, when nitrogen is reacting with oxygen, we will get different oxides. Most generally, let us generalize a metal like element as M. It can form M2O3 type oxides, M2O5 type oxides, because here it is +3 oxidation state, here it is +5. So we will get two types of oxides here. Okay. So yesterday's class discussion I told you, if more oxidation state, what I am saying, if oxidation state increases, acidic nature also increases. So between E2O5 and E2O3 type oxides, which is more acidic? E2O5 is acidic. Okay. Now see, I have written some more oxides. So which is more acidic here? More the oxidation state, greater is the acidic nature. Okay. Like that, you have this type of oxides first. What is the oxidation state here you are seeing? +3. Crisscross method you do. +3, -2. This one +4, -2. Here it is +5. So between these three, which is more acidic? Like this you can say. Okay. Next, you need to make the list of these oxides. First two are non-metals now. Nitrogen, phosphorus, they will form acidic oxides. Next two are, they are forming amphoteric oxide. Last one is metal, forms basic oxide. Okay. For which type of oxide it is? E2O3, like N2O3, P2O3 type oxides. Next one, E2O4 type, all of them are acidic, because oxidation state increases now, acidic nature also increases. All of them are acidic. Now all of them are having +4 oxidation states only now. Now look at the element electronegativity. More electronegativity, more acidic nature. Which is electronegative element out of this? Nitrogen. The next, phosphorus. That's why their oxides are acidic oxides, strong acidic oxide. Next one, weak. This one very weak. Clear everyone? Okay. Next thing here, if you observe, E2O5 type if you consider, like N2O5, P2O5, very strong acidic oxide, next strong acidic oxide, weak acidic oxide. Okay. So now how can you remember them in a simple way? Tell me. E2O4, E2O5 type, all of them are acidic. Down the group acidic nature decreases. Next, E2O3 type, first two are acidic, next two are amphoteric, last one is basic. Remember like this. Write this list. stability of oxides, if they ask, stability of oxides varies like this. Down the group stability of oxides decreases, you can write. So N2O3 is more stable, the next N2P2O3, like that you write. Stability of oxides. Okay, so we are studying it as acidic oxides, basic oxides, amphoteric oxides now. So when you do an acidic oxide hydrolysis, what you are doing? You are taking an acidic oxide, you are adding water. You are going to get an oxo acid. What you are going to get? Oxo acid. Simply you can remember it as acid. Okay, and if you are doing a basic oxide hydrolysis, you are going to get base, like hydroxide you are going to get. We will see one example, hydroxide you are going to get. For example, N2O5 is acidic oxide or basic oxide, tell me? Strong, very strong acidic oxide, no? So if you hydrolyze this, you are adding water. What is the oxidation state of nitrogen in N2O5? +5. You will get respect to acid. With +5 oxidation state, you have nitric acid now. So HNO3 is your product. See, HNO3 is acid or not? So now tell me, acidic oxides upon hydrolysis gives you acids, or simply you should say oxoacid. Next one, basic oxides upon hydrolysis gives you hydroxides. Those are nothing but bases. Okay, so you can take any basic oxides like Na2O. If you take, if you hydrolyze, what you are going to get? NaOH, like this now. NaOH is a hydroxide now, base only now, like that. Okay. So here I have mentioned that statement. Acidic oxides upon hydrolysis gives you oxoacids. Okay. So here you have N2O3 type. What is the oxidation state you are seeing? +3. So with +3 we have nitrous acid. +3. So nitrous acid is the acid formed here. Okay. With +5, nitric acid. Okay. Similar to that, here P2O3 is there. This is also acidic oxide. You will get with +3 oxidation state phosphorus acid or orthophosphorus acid, you should say. Okay. Remaining these two are what? Amphoteric. So amphoteric compounds can react with both acids as well as base. Okay, and forms respective salts. See, what is the oxidation state of this arsenic here? +3. So forms respect to salt because it is treated with what? Acid. So amphoteric compounds upon treating with acids forms salts. Even if you treat with base also, it will form salts. Okay. With the same oxidation state, they are forming the products. Okay. Now look at this. N2O3, what is the product formed upon hydrolysis? HNO2, nitrous acid is formed because it is +3, here also +3. N2O5 forming nitric acid, +5, +5. Now I am saying here N2O4. What is the oxidation state? This is also acidic oxide now. You should get respect to acid. With +4 we do not have any acid for nitrogen. So what it will do is, it will form a product with one lower oxidation state with one higher oxidation state. So with one lower means +3 oxidation state, +5. So the products formed here is HNO2 and HNO3. Okay, when it is with the intermediate oxidation state. Okay. Yeah. Next. So this is the thing we have discussed. N2O4, if I hydrolyze, what we are getting? One +3 oxide acid, +5 acid. So it is giving mixture of acids now upon hydrolysis. So you should call them as mixed anhydrides. So mixed anhydrides upon hydrolysis gives you mixture of acids. So you can write this reaction, one reaction. Okay, done. See, I have an acid with +5 oxidation state, oxide with +5 oxidation state. So what will be the product? Acid with the same oxidation state. So N2O5 gives you HNO3. P2O5 gives you H3PO4. Find the oxidation state, you will get the +5. Okay, similarly this one also, arsenic also. Okay. See, if group 15 elements reacting with halogens, they will form two types of compounds with +3 oxidation state and with +5. So what are the two types? Like MX3 type and MX5 type. Okay. Now remember, can nitrogen form MX5 type? Because in order to form MX5 type, how many bonds required? 5 bonds. But nitrogen covalence is how much? 4. So it can only form NX3 type of compounds. What type of compounds? NX3. And out of that NX3, all halides are unstable except NF3. Which is stable here? Only NF3. All other halides of nitrogen are unstable. Which one is stable? NF3. Okay. Next, let us say phosphorus. Yeah, phosphorus can form PCl3 type, like MCl3 type, and PCl5. Both are possible now. What is the hybridization here in PCl3? sp3. sp3. What about PCl5? sp3d. What is its sp3d? What is its geometry? PCl5 means trigonal bipyramid. There are two types of bond lengths. Remember that line we have discussed during axial and equatorial. Which bond is more longer? Axial bonds are longer than this. See, these above below lines are called axial lines, axial bonds. Okay. So what about this one? With 120 degrees are there now. These are called equatorial. Okay. Remember this. Next. This is a story we have here. Next. Okay. Now down the group you tell me, I have PCl5 to BiCl5. Which is stable? Down the group, what happens to the stability of these compounds? Decreases or increases? Decreases. Why? Because +5 oxidation state is unstable for bismuth now because of inert pair effect. So stability decreases down the group, you can understand in that way. Okay. Next, when it comes to PCl5 or PBr5, so PBr5 in the solid state, what I am saying? PBr5 in the solid state exhibits like this. PBr5 dissociates as PBr4 and Br. So write this. So they will ask, PBr5 in the solid state exists in which are the following manner? PBr4 plus Br minus. Okay, next. Whereas PCl5 is there now, PCl5. So PCl5 in the solid state exists as a dimer, whereas PBr5 monomer with the tetrahedral geometry, PBr4 plus. Whereas PCl5 in the solid state dimer. So dimer means like this now. So it dissociates like this, PCl4 plus PCl6 minus. Okay, so one is tetrahedral geometry, other one is octahedral. Next. Over? Okay. So when these 15th group elements like nitrogen is reacting with alkaline earth metals, forms respective nitrates, calcium nitrate, okay. If it is calcium with phosphorus, calcium phosphide, like that we will get the products, okay. Next. This you know. So what is the bond order of nitrogen? bond order in the nitrogen. Like how many bonds are there in N2? Triple bond now. So bond order is 3. Now I am converting from N2 to N2 place. What happens to the bond order? Decreases or increases? Decreases. Here what is the bond order? 3. Here it becomes 2.5. This thing we discussed in the molecular orbital theory. Okay, right. So now what are the preparation methods we have for nitrogen? So first one is laboratory preparation. Here ammonium chloride treated with NaNO2. Write these 3 methods. So first one is what? Ammonium chloride with NaNO2 gives you N2 plus 2H2. So N2 gas is liberated. Okay. So during this process, small amount of NO, HNO3 are also formed. Okay, what are formed? NO, what are the byproducts? NO, nitric oxide, and HNO3, nitric acid, are formed as an impurity, and this can be removed by passing through what? Aqueous sulfuric acid containing potassium dichromate. So what is the laboratory method we did? Ammonium chloride with NaNO2 gives you N2 plus H2O. During this process, NO and HNO3 is formed as byproducts. This can be removed by treating with aqueous sulfuric acid and potassium dichromate. Next method is decomposition of ammonium dichromate. What is that? Second method is what? Decomposition of ammonium dichromate. Ammonium dichromate upon heating releases N2 gas. What it is releasing? N2 gas. Along with that, Cr2O3 and water are formed. They will ask you what are the products formed during the decomposition of ammonium dichromate. What are the 3 things formed? N2, H2O, Cr2O3. Write the reactions as it is. Okay, last reaction. In order to get very pure nitrogen, what I am saying, in order to get very pure nitrogen, we will be using it from azides, like metal azides will be there na, sodium azide, barium azide. It means NaNe3 is called what? Sodium azide. So with barium means like second group element now, so it will be twice. So sodium azide, barium azide, upon heating you are going to get a pure nitrogen. Okay, so pure form of nitrogen can be obtained from which are the following reaction they will ask. From where? From azides, like metal azides you remember. And one more thing, one important application of this sodium azide is, you know, cars. In that, what name? Airbags. Like accident, if anything is happening, like cars will be having what? Airbags. So airbags will open up, na? So what it contains? It contains sodium azide, like NaN3. So there will be one spark, because spark untundi. Accident vehicle ki edaina accident avvagane a spark ignite chestadi. So when you are heating this, what happens? It will be giving you huge amount of N2 gas. So by that air balloons will get blown up and it will be protecting the passengers. This is an important application of sodium azide. Okay, the next one from urea. So urea upon treating with nitric acid gives you N2, CO2 and H2. What is another process? Urea with nitric acid. So what are the products formed? N2, CO2, H2. What is the formula of urea? NH2 taken twice, CO. CO, NH2 taken twice. Okay, next. Okay, this reaction again important. Calcium carbide with what? Calcium carbide with N2 forms like calcium like NCN. So this is called a nitrolim. What is this? So it is a fertilizer. What is it? It's a fertilizer. So you write this reaction. It can also be indicated like this, CaNCN2. Both of them are same. Whereas barium carbide with nitrogen forms barium cyanide. What it is forming? Barium cyanide. Write these two reactions. Okay, next. Next. Okay, now what are the compounds of nitrogen? Well known compound is ammonia. So how can you prepare ammonia? First one is from urea. This is general method. So urea upon treating with water, what happens? It will produces ammonia. Once again, urea upon treating with water produces ammonia. So NH3, H2O, CO. Whereas urea with nitric acid, N2 plus H2O plus CO2. Urea with water, ammonia gas. Ammonia, H2O, CO2. Okay. So the next one, laboratory methods again. Write all these laboratory methods. So first one is from where? From ammonium chloride with base. See, ammonium chloride is a salt. Na? How this salt is formed? From a weak base like ammonia and a strong acid like HCl. Okay, so this HCl from here will react with this and gives you ammonia back. Same story here also, ammonium chloride with CaOH twice gives you ammonia and respect to salts like CaCl2 and H2O. Same here also. Okay, so now what is the largest scale like industrial method of preparation of ammonia is by Haber's process. What is that? Haber's process. What are the raw materials we'll use there? N2 and H2. Now, okay. So do you remember Lee-Chatterjee principle? Oh. What are the favorable conditions for the forward reaction? It is an exothermic reaction now. So low temperature, pressure, however, what about pressure? High pressures, low temperatures and high pressures are the favorable conditions as per the Lee-Chatterjee principle. Okay, now industrially when they are preparing ammonia, what are the optimum conditions? Means suitable conditions. So temperature should be 700 degrees, 700 Kelvin, pressure should be high pressure, not 200 atm pressure. So what is the catalyst used during the Haber's process? Iron. Iron with K2 and Al2O3. So what is the promoter? Molybdenum. You already written this, I think so. Okay. Next. So ammonia, what are the characters it has? It's chemical properties. It's a weak base now. So weak base means reacts with acids, forms respective salts. Okay, like ammonium sulfate, ammonium chloride, ammonium hydroxides with water. Okay, now just now you have seen ammonium chloride. If I treat with NaOH, tell me what is the product formed? Ammonium chloride with NaOH. I told you, while produces ammonia gas plus NaCl plus H2. Similarly, here also you will get the same kind of products. Okay. Next. Okay, from here you can expect this table now, important. What are the oxides we have for nitrogen? Write this: N2O, NO, NO2 or N2O3, NO2, N2O5. You can write the table later, but just listen to me first. Out of all these, first two are neutral. What I am saying, first two are neutral. Remaining all oxides are acidic. Which is stronger acidic? Strong acidic, N2O5. Okay, remember this. Next one, they will ask you what type of bond present in N2O5. Firstly, they will ask you about oxidation states. You know now, here what is oxidation state? +1, this is -2. Oxides means always oxygen should be -2. So, remaining element will be positive charge. Here it is +2, -2. So, you make this crisscross, +3, -2. Here +4, -2. Here +5, -2. Done? Next. Whenever you are seeing here, what is the maximum oxidation state of nitrogen? Remember this important trick to remember all the time. Whenever an element oxidation state is equals to maximum oxidation state, there exists MOM type of bond. Which type of bond it will be? MOM bond. If element oxidation state is less than maximum oxidation state, direct MM type of linkage will be there. What type of linkage? MM. It means, sir, what you are saying we are not getting now. I will tell you. What is the oxidation state? Here we have +3 now. So in +3 case, which statement valid here? First statement. Element with less than maximum oxidation state, what type of linkage? It means direct nitrogen linkage will be there. So how many oxygens are there here? 3. So you can give it like this, like this, like this. Here what is the oxidation state you are seeing? +5. So if +5 oxidation state, what type of linkage will be there? You put nitrogen here, one more nitrogen here, oxygen in between. Okay, still how many oxygens are there? 4. Give it one here, second one over here, like this. So with these lines, what you have studied, if oxidation state of an element is maximum oxidation state, there exists an oxy linkage. What type of linkage? If oxidation state is less than its maximum oxidation state, direct linkage, MM linkage, like element to element linkage. Okay, sometimes we will see oxidation state, calculated oxidation state is greater than the maximum oxidation state. Here it is equal, this is less. What is the third condition I am saying? Greater. So in that case, you are going to see peroxy linkage. What type of linkage? If calculated oxidation state greater than maximum oxidation state of element, what type of linkage you are going to see? Peroxy linkage. Okay, write these 3 points, these points if required, otherwise I will move forward. Move forward? Okay. So what are the oxides of nitrogen neutral? Remaining all are acidic. Remember that. Okay, let's move forward. Okay, so the next one, nitric acid. How can you prepare nitric acid? Like what is the industrial method, and important question you have in the exam is Ostwald's process. So what is the raw material you are using there? Ammonia, and it involves 3 steps. How many steps it involves? 3 steps. First one is treating ammonia with oxygen, like oxidation, catalytic oxidation of ammonia by atmospheric oxygen. So during this process you will use a catalyst. What is that catalyst? Rhodium platinum gas. Okay, what is the temperature you are mentioning? 500 Kelvin, 9 bar. Okay, now what is the compound formed here? NO, carbon monoxide, nitrogen monoxide. Okay. So that nitric acid, that like nitrogen monoxide, again further oxidized to nitrogen dioxide. So nitrogen dioxide you are hydrolyzing. What you are doing? Hydrolyzing. Nitrogen dioxide formed is dissolves in water to give you HNO3. Okay. Again, what is the byproduct formed? NO, that also formed in the first step now. So this can be again recycled. Means get oxidized to NO2, gives you HNO3 upon hydrolysis. Like this, it will be recycled. That's it. So what is the catalyst used here in the process? Platinum or rhodium gas. Next. So what are the points to be remembered here? Nitric acid will be concentrated by distillation process. Okay, that's it, that's it. Okay, so when you use nitric acid, if it is falling on the skin, it causes a painful blisters and the skin color changes to yellow. It means the skin will get oxidized, the proteins will get oxidized to xanthoprotein. What is it? Xanthoprotein. So what is the color you are going to see? Yellow color. Like this, xanthoproteins it will be. Yeah. Next, if you are treating nitric acid with any of these elements, gets respective acids and oxides. See, carbon forms carbon dioxide. What is the gas released? NO2. All these elements you remember, carbon, phosphorus, sulfur, iodine, all of them are giving what gases? NO2. So the table I told you to write later now, it also shows which is paramagnetic gas, which is diamagnetic. So NO2, if you observe, it will be like this one. It has one unpaired electron now. So it's a paramagnetic gas with a brown color. What is the color of the gas? Brown. Remember this very important point, they may ask you. They will ask you like this. Carbon upon treating with nitric acid releases 2 gases. What are the 2 gases? And one of that gas is brown color. Both of them are CO2, gases like CO2 and NO2. Which is brown color gas here? NO2, like that. Yeah, next. See, reaction with metals. Reaction with metals here. Copper metal if you take, you treat this with dilute and treat this with concentrated. You will get both carbon, like copper nitrates only, but the gas released is different. So in which case the brown color gas is released? Concentrated case. So it will be NO2, concentrated case. In the dilute case it is NO. Both NO also paramagnetic. Why it is paramagnetic? See, nitrogen contains odd number of electrons now. So nitrogen 1, 2, 3, 4, 5. So oxygen 6 electrons in the valency. You make a bond like this. See, still how many electrons are there? 3. It means odd electron is there now. So it can be also a paramagnetic. Okay, fine. Next. So there are some metals will not react with nitric acid, I told you. What is the first element we discussed like that? Due to passivity, I told you. Aluminium. when I told you about the discussion of aluminium, aluminium does not react with HNO3 because it forms a protective layer, that is called passivity. Not only aluminium, the diagonal relation one, what is that? Aluminium and beryllium and chromium, nickel. So these four elements does not react with HNO3 because they forms a protective layer. The process is called what? Passivity. Write these four elements and just mention it does not react with HNO3. Okay. So next one, all of you know goldsmith. You use ornaments now. Okay, gold and silver ornaments. Okay, so these gold and silver ornaments, first of all, they won't dissolve in nitric acid. What I am saying, they won't dissolve in nitric acid. But if you convert into an aqua regia, what is that? I am saying aqua regia. Now it can be dissolved. What is the thing we need to use? Aqua regia. So aqua regia is nothing but mixture of nitric acid and HCl. What is the mixture? Nitric acid and HCl. So you just take some metals like platinum, rhodium, iridium, rhodium, called noble metals, insoluble in nitric acid but soluble in aqua regia. They will ask you what is this aqua regia means. You take 1 mole of nitric acid, 3 moles of HCl. So 1 mole HNO3 plus 3 mole HCl. 1:3 ratio of nitric acid and HCl is considered as aqua regia. So these in this aqua regia, yeah, these noble metals get dissolved. Okay, remember this. How can you remember the noble metals? Just remember them as pair: platinum, rhodium, iridium, rhodium. What is that? Platinum, rhodium, iridium, rhodium. So what is the composition of aqua regia? HNO3 and HCl. What is the purpose of it? To dissolve noble metals. Next. So nitric acid independently also called as a strong water. What I am saying? Strong water or aqua fortis. What is that? Aqua fortis. Because it dissolves all types of salts. Nitric acid also called as, what are the names it has? Aqua fortis or strong water. Strong water, why we are saying like that? Because it able to dissolve all types of salts. Next. Next one, done? Okay, so now what about brown ring test again? It is used for what? Nitrate ion conformation, right? So nitrate ion with freshly prepared ferrous sulfate in sulfuric acid medium, it will form NO, nitric oxide. So this nitric oxide with that iron like ferrous sulfate solution converts into this form. What is the formula of brown ring complex now? FeH2O 5 times NO plus. What is the charge on NO? It will be plus 1. NO charge is plus 1. What is the oxidation state of iron? Plus 1 in the brown ring. Remember these 2 points. What is the formula? First you remember. Then next remember oxidation state of iron in the brown ring test. Okay, next. Last discussion. See, next phosphorus, allotropes of phosphorus. We have, see this. Remember. Okay. Both, no? Okay. So what are the allotropes for phosphorus we have? White phosphorus, red phosphorus, black phosphorus. So white phosphorus, what is the atomicity they will ask? It will exist in tetrameric form, P4. This is polymeric. This is of two types, black, alpha black, beta black. Okay, so now how it will be? White phosphorus is a white, soft, waxy. Next, this is a brittle powder. And white phosphorus has a smell like garlic. What type of smell? Garlic. Next one, red phosphorus is insoluble in water, I am saying. It's a odorless, insoluble in water. And red phosphorus is less reactive, I am saying. What is less reactive here? Less reactive, it means more stable. Comparatively more stable than this white phosphorus. Okay, remember this. Next, you just remember these oxides. Structures of oxides of phosphorus. See, we have seen P2O3 now. What is the dimeric form of P2O3? This is an EAPCET question, that's why I am doing. Dimeric form means P4O6. Okay, so P4O6 structure they will ask. So what you need to do is arrange 4 phosphorus atoms like this. How many oxygens are there? So put like this each time. How many over? 4. One more like this, one more like this. Okay, now nitrogen, how many lone pairs are there? 1. So now check what is the hybridization of each phosphorus here, not nitrogen, phosphorus. sp3 only. Now how many POP bonds are there in the given compound, they will ask. 6 POP bonds will be there. Okay, this is P4O6. Next case is P4O8. Extra how many oxygens we are seeing there? You insert one oxygen over here, other one here. P4 POP, number of POP bonds again how many? 6 only. Extra what they have added? So P double bond O, how many bonds? 2. Next compound is P4O10. Now you put one oxygen here and another one is here. POP bonds again same, but what is changed? P double bond O. How many are there? 4. That's it. Remember it like this. Okay? Yeah, these are the oxides I told you about. POP bond 6, PO linkages. How many PO linkages if I ask? 6 means 6 into 2 becomes 12. Okay? Right. So these are monomers, dimers. We have discussed about dimers. That's it. Next one is, look at this. Like P4 form for the phosphorus. So I am treating this with base. What I am treating? Base. What is the oxidation state of phosphorus here, you tell me? When an element combined with itself, oxidation state will be 0. So we are doing the reaction in basic medium now. You are going to get product as PH3. What you are going to get? PH3. So PH3 is called phosphine. What is this? Okay. Next, along with that, what is the byproduct? H2PO2 minus. Minus, instead I am writing sodium here. So sodium hypophosphite. What is the name of that? Sodium hypophosphite. What is the oxidation state of phosphorus here? Minus 3. How much? Minus 3. In this case, how much it is? Check once. Plus 1. Okay. Now a 0 number converting into minus 3 and plus 1. What is the process I can say? Disproportionation. So now tell me, P4 phosphorus in basic medium undergoes disproportionation reaction and forms phosphine like PH3 and NaH2PO2. Okay. So what is the oxidation state here? Plus 1. Remember the 2 oxidation states. Okay. So next one, like have you seen like some fishermen or some like whoever in the coastal region goes to fishing or some other purpose in the ship right now. So they used to give signals. Okay. So for that signaling purpose, they will use calcium phosphide. What they will use? Calcium phosphide. So this calcium phosphide, when you are throwing in water, where you are throwing in the water, it will releases PH3 like phosphine. Okay. This and like these are the 2 products formed. Now it is catches fire when it is in touch with the water. So with that signal they can identify, oh, there is some persons doing something like that. So this signaling process is called Holmes signal. What is that? Holmes signal. So what is used in Holmes signal? Calcium phosphate. Remember that. Okay. Next. Group 16 is there. Okay. So what are the elements in group 16 we have? Fast. Oxygen, sulfur, selenium, tellurium, polonium. So we can call group 16 elements also as chalcogens. Chalcogens means what? Ore forming elements. Because most of the ores, if you see, either they are the oxides or they are the sulfides. That's why most of the ores exhibits either oxides and sulfides. No? That's why we are calling these elements as what? Chalcogens. Chalcogens means ore forming elements. Okay. So now what I am saying? First two are again non-metals, next metalloids, last one metal. What is the general electronic configuration for this? NS2, NP4. So now it can like all of these compounds, like mostly they wanted to be in -2, like oxygen especially. If oxygen is -2, you should say it as oxide. What you should call? Oxide. Okay. Now let us discuss periodic properties first. What about atomic radius and ionization energy? Atomic radius down the group increases, ionization energy decreases. Compared with 16th group and 15th group, who is having more ionization energy? 15th or 16th? Why 15th? Because of half filled electronic configuration we discussed. Between oxygen and nitrogen. Nitrogen. Okay. Next one is electron gain enthalpy. Again you can expect this question. Electron gain enthalpy order we discuss in the periodic table. Which is highest? Sulfur. The next selenium. Like that it goes on down. Least you put oxygen. Okay. So similar to this halogens also you tell me. Fluorine, chlorine, bromine, iodine I am saying. Which is having highest electron gain enthalpy or electron affinity? Chlorine. Next bromine. Next iodine. No. Fluorine. Next bromine. Next iodine. Here sulfur, selenium, tellurium, polonium, and least is oxygen. Remember this two order you can expect here one question. Next. Done? So down the group what happens to electronegativity? Decreases. Oxygen is the second most highest electronegative element in the periodic table. So that's why whenever oxygen is combining with all other elements, oxygen will be with a negative oxidation state, like either -2 or -1 or -half. Okay, but when oxygen is combining with fluorine, with what? Fluorine. So oxygen will be in the plus oxidation state. If it is OF2, what is the oxidation state of oxygen here? +2. It is O2F2 +1 for each oxygen. Remember this. When oxygen shows positive oxidation states, when it combines with the fluorine only. Okay. So if oxygen is -2 oxidation state, like O-2, you should call it as oxide. What is it? Oxide. If it is like this, H2O2 you are saying, what is the name of this compound? Hydrogen peroxide. No? So in peroxide form, what is the charge on each oxygen? -1. So this is peroxide. If I say superoxide, superoxide means O2 -1, like KO2 you are writing. So K plus O2 minus. So on one oxygen what is the charge you are saying? 2 oxygens -1. 1 oxygen -half. So if it is -half, oxygen with -half, you should say it as super oxide. Okay. Now I am writing O2, O2 minus 2, O2 minus 1. So tell me which is having higher bond order out of this? How to say this? Molecular orbital theory. So count the electrons. O2, O2 minus 1, let us say O2 minus 2. Tell me here, count the electrons. O2 means how many electrons? 16. Here 17. Here 18. So what I told you, 14 electrons, bond order 3. 15, 2.5. 16, 2.0. So this is bond order is 2.0. Between O, two bonds will be there. Okay. 17. Like this, what happens to the bond order? Decreases. So highest is like this. Bond order. Bond order directly proportional to bond strength also, and inversely proportional to bond length. So if I ask for bond length, order will be reverse. Clear? This discussion we did in MOT. Clear or not this discussion? Yeah. So all elements of group 16 shows allotropy. Okay. What are the allotrope forms of oxygen? Oxygen, like oxygen molecule, O2 and O3 are the allotropes. Okay. Next, for sulfur, it will be orthorhombic monoclinic, we will say, like S8, and it can be S6 also. For sulfur, what are the allotropes we have? S8, S6, like that. Now what are the oxidation states? It can show oxidation states from -2 to +6. What are the possible oxidation states for this? -2 to +6. Okay. This one is discussed, done. Next. But oxygen shows what is the maximum oxidation state? Positive oxidation states. +2. Okay. Next. Okay. So what is the general electronic configuration? Once again you tell me. NS2, NP4. If I use all 6 electrons, it will be +6. If I only use this NP electrons, +4. Okay, down the group +6 oxidation stability decreases, +4 oxidation stability increases. What is the concept? Inert pair effect. Okay. Next, hydrates we discussed. What about the stability of hydrates down the group? There also I explained already in 15th group. See, hydrates of 15th group or 16th group? Definitely one question. Tell me down the group what happens to the stability? Decreases. Stability decreases. What I told you about acidic nature? Increases. Acidic nature increases. What about stability decreasing means bond strength? So bond dissociation energy also decreases. Reducing character increases. There also increases, here also increases. Bond angle, what I told you? Decreases. This is around 104 and it becomes around equals to 90. So what is happening down the group? Decreasing. Next. You can write these orders. Done. Next, melting point and boiling point. What I am saying, melting point and next, melting point and boiling point should increase with increase in molecular weight. So it means highest melting point and boiling point should be the hydrate, bottom hydrate, because more molecular weight. Okay. But exceptionally water is highest. Why? Because of hydrogen bonding. There also ammonia, here it is water. What is the reason for that? Intermolecular hydrogen bonding. So both the melting point, boiling point is highest for H2O. Remaining is like this. First you write with respect to molecular weights, then insert a water molecule at the top because of its hydrogen bonding. Oxides, if you say, we have two types of oxides with +4, +2, like SO2, what is the oxidation state? +4 for the sulfur. SO3, +6. So two oxides are there. Which is more acidic? SO3 type is more acidic because higher oxidation state. Next. Down the group, for example, SO3 is there. Like that I am going up to oxygen, sulfur, tellurium trioxide. Which is more stable oxide out of this? SO2, because +6 oxidation state down the group, what happens? Like that. Okay. Next, acidic nature we already discussed. Okay, halides. What are the types of halides we can have? like it can be two types, I mean like this, SCl2 or OCl2 type, like this. Next it can be SCl4, SF6, we are writing like this now. So how many possibilities are there for halides? X2 type, X4 type, X6 type. Down the group, X6 type stability decreases. Why? +6 oxidation state. That's it. Next. This is fine. Next. You know chemical bonding, studied about hybridization now. We can expect a question from that hybridization again. For example, here I am saying OCl2. What is the hybridization of oxygen? Okay, and here SF4 I am seeing. Here SF6. Tell me fast. So what I told you here, how to find? Group number is 16. So 6 valency electrons. 6 plus 4, 10. 10 by 2. 5. 5 means trigonal bipyramidal geometry should come. But out of this 5, how many surrounding atoms are there? 4. So 4 means how many lone pairs will be there? 1. So with trigonal bipyramidal geometry, 4 atoms, 1 lone pair. Lone pair should be placed at axial or equatorial? Equatorial. See, I told you 2 positions, like when I am saying about phosphorus. So these positions are what? Equatorial position, you put lone pairs. Why to put in the equatorial position? Because there is maximum angle now. So lone pairs should be kept with maximum angle. Therefore it will be more stable. So like this you get. What is the name of this structure called? Like this you are removing one bond. Seesaw. What is that? Seesaw or distorted tetrahedral. What is that? Distorted tetrahedral or seesaw. Next SF6 you will get an octahedral geometry like this. Okay, next. Oxides. So look at the oxides. We have CO2, SO2 like this. So greater the oxidation state, greater is the acidic nature. Next, more is the electronegativity, more is the acidic nature. Based on this, we have acidic oxides, basic oxides, amphoteric. So acidic oxides examples like this. See, these are non-metals. Non-metals forms acidic oxides. Metals forms basic oxide. Metalloids forms amphoteric. So these are some examples. Even some metals form acidic oxides. What I am saying, generally what we know metals means they should form only basic oxide. Which type of metals? Either alkali metals, alkaline metals are there now. Those forms only basic oxides. In alkaline metals, here beryllium oxide is there now. So this is also amphoteric. What I am saying, this is also amphoteric. Remaining all are basic oxides. When it comes to this D block elements, metals are there now, like MnO7 is there, Mn2O7. This is again acidic oxide. It means in the metals also, with a higher oxidation state, they will form acidic oxide. What is the oxidation state here seeing here? +7. So with the highest oxidation state now, so what is the nature of this oxide? So that's why I am saying if oxidation state increases, acidic nature also increases. See, for example, I am writing MO2, MnO2, Mn2O7, which is acidic here or stronger acidic, like this. Okay, next. Ozone structure will be written as O3. Okay, and these are the resonating structures. The bond length will be same. And what is the oxidation state of each oxygen in ozone? Ozone now, same element combined with itself. 0. Okay. Allotropes of sulfur. Two allotropes I told you. Monoclinic, rhombohedral, like rhombic. What are the two allotropes? Monoclinic, rhombic. Okay. You just see these two structures exist in a stable form. Both forms are stable at a particular temperature. What is the temperature value? 369. What are the two forms we have? Monoclinic, rhombic. Both structures are stable at what temperature? 369. Just look at the structures. S8 having what structure? Cone shape. S6 having chair. Remember the structures. S8 cone. S6. That's it. Remaining things we'll see questions and some remaining portion in the next session. Thank you.